In RF and microwave engineering, engineers are facing unprecedented workloads in the form of tight deadlines, numerous projects, and pressure to reduce costs. EM simulation play a critical role in RF product and wireless design for modern engineers. For communications and radar systems, including Wi-Fi, 5G, upcoming 6G, radar for automotive, in-cabin, indoors, and satellites. In today's talk, we are focused on the utilization of Remcom simulation software for numerous use cases, including device design, cellular antennas, matching, and automotive radar design, placement, and the use of propagation software for analysis of those electrical and electronic devices. My name is Surun Chavla. I've been at Remcom for over 15 years, working with engineers across the consumer electronics space, automotive, satellite, and the Department of Defense. I will be giving this 10 to 15-minute talk focused on the use of simulation and how we are working very closely with world leaders, including NASA, in the space of wireless communications to accelerate the ability to simulate and automate the issues that engineers face on a daily basis. This talk, labeled RF Wireless System Digital Twins, will explain what digital twins are and how automation is used for machine learning and for artificial intelligence in the spaces of RF and microwave. To begin the context of this talk, computational electromagnetic models have been developed since World War II and have expanded in the use case-driven approach, which is primarily antennas, antenna placement, circuits, and signal processing. In modern technology, we have the use of novel materials, metamaterials, reconfigurable intelligent surfaces, and materials used for cloaking, for radar, and for upcoming use cases, including grid lenses and so on. Fundamental to all of this is physics-based models, namely finite difference time domain, FDTD, as shown in blue, in green. And in blue would be lower frequency use cases, namely quasi-static and static. And use cases in purple and red would expand as high-frequency methods, asymptotic methods, namely physical optics, method of equivalent currents, geometrical optics, uniform theory of diffraction would be used. The ideal case is where large use cases where devices are placed in environments, namely a user walking in an urban environment with a phone in their hand and using, say, millimeter wave 5G or using low band 5G, and understanding the behavior of that user as they experience their device being utilized in a very complex environment where multipath plays a critical role. And this can be expanded, this type of mindset can be expanded to user experience down to the throughput level or megabits per second. So how do we go from the input signal at the circuitry to the RF, to the device, to the user, to the base station in the environment, and then understand how the device will behave in field testing, in lab testing, including OTA chambers, over-the-air wireless chambers. It's our measurements for exposure, and then we have measurements for various types of chambers. So finite difference time domain is a transient method which uses Maxwell's equations and solves for fields on the mechanical device that the engineer imports into the software. So we'll see a few use cases like showing how simulation tools, namely XFdtd, developed by Remcom over 30+ years, help in this regard. And then as we go up in electrical size, methods like FDTD, FEM, finite element method, require additional computational resources, which are not available typically for even at enterprise level engineers, may require numerous GPUs, and runtimes would be untenable. So we use methodologies that provide some level of accuracy with assumptions of far field and the assumptions of large scale deployments. So we'll be learning about a little bit about hybrid technology that we've been developing with Huygens. As mentioned earlier, the use of simulation tools has been around for over 40 or 50 years, namely in finite element method, finite difference time domain, with physical optics, uniform theory of diffraction, and geometrical optics. Now, Remcom has worked hard over the past 30 years to develop and lead these different spaces to be able to enable engineers to make their designs in a fast turnaround time. XFdtd is one of the world's premier finite difference time domain solvers, allowing engineers to design, analyze antennas, their RF systems, including the effects of biological tissue, radar cross-section, and use cases in the photonics region. As electrical sizes grow, this would be many wavelengths by many wavelengths, utilizing the NVIDIA GPU, and solvable on a laptop all the way to compute clusters with tens, if not hundreds of GPUs. We have yet to find an upper limit on the amount of memory that XF can utilize. The largest problem we have run is north of 10 terabytes of GPU memory, and we have yet to hit its limits. Phased arrays and, of course, Raman lenses are one of the growing areas of communications with ultramassive MIMO, with upcoming 6G, and the utilization of beamformers. Wayfarer and Wireless InSite are tools that Remcom is developing for different use cases, namely radar and wireless communications with 6G ISAC. We have the use cases of radar still in the presence of communication systems, and potentially for multi-purpose use for radars, potentially for other use cases, including monostatic, bistatic, and indoor. So we have enabled users to model FMCW waveforms inside Wayfarer using physical optics, where we illuminate and target a access point and provide the backscatter from a target inside an environment. So this is a see-through wall radar use case where there is a person behind the wall, and this radar is able to get the multipath correct all the way to the target, the scattering from the target, and the multipath back from that target to the receive radar, to the receive antenna of the radar. Automotive use cases outdoors are simpler in that case because multipath is really mostly from the ground, from the rough ground, and the vehicle in front, and then potentially some on the way back. So transmissions are not very much of a big concern. However, transmissions for indoor use cases present a large challenge in terms of multipath. Wireless InSite, world's leading RF channel modeling software, developed for the DoD in the late 90s, has come to be a standard for ray tracing. We have developed multipath, geometrical optics, UTD, image theory, and other techniques to be able to accurately predict the behavior of wireless systems in very complex environments, including NTN, SATCOM, and indoor, outdoor, the first 5G trials, for example, and massive MIMO. We're also working very closely with NASA to develop LunaNet, which is the internet deployment of 4G, 5G, 6G, Wi-Fi, potentially on the moon. Furthermore, we're looking at communications between astronauts with the utilization of placement of antennas on the suit, and looking at side link of communications between astronauts, which utilizes fields that are simulated using XFdtd or measured in a chamber, namely from MVG, and we bring those over into the simulation space with the material, with the de-embedding, and place that near field source, including the antenna and the tangential E and H fields of the antenna on the body, and place it in the environment that could be on the surface of the moon. It could be on a rover. And for generic consumer electronic use cases, on-body antennas, namely smartwatch to phone and GNSS to smartwatch in an urban area. Moving forward, the markets we serve are devices in the consumer electronics space. We have had the immense pleasure to work with our key partner, Motorola, for over 30 years. And the number of devices that have come out collectively that have been designed with Remcom's tools are now in the 3 billion plus range in terms of manufactured devices and consumed devices. Smartwatches from Garmin, Alexa products, Dell laptops, Google Pixel phones are another adjacent use case for XFdtd. The challenges in consumer electronic spaces include the reliance on matching and circuit matching, with the synthesis of the matching network to tune and match antennas, numerous antennas, about 8 or more. And these antennas require isolation, they require exposure studies, and they require the correct component values to be able to tune and match for specific bands, potentially in the 30 to 50 5G bands. Doing that inside XFdtd with the circuit schematic functionality is extremely powerful. Moving into higher frequencies with 24, 77, 83, D-band 94 plus gigahertz, we have been working with automotive manufacturers for numerous years to be able to design and place devices for automotive radar use cases, including adaptive cruise control, and for long-range detection of vehicles in driving scenarios. As of the past 4 years or so, we have been working closely with tier 1 manufacturers in placing radars inside the cabin for child detection, potentially putting radars on the roof of the car, on the rear view mirror to be able to detect for CPD, for child presence detection. So automotive is a growing area, and we're developing complex solvers to be able to solve this extremely challenging measurement and digitized issue with automotive engineers. Fundamental to our business is our commitment to the Department of Defense in the U.S. military, including the U.S. Army, the U.S. Air Force, and our development of the Empire program, which includes 20 plus different models that Remcom has maintained and developed for the Naval Research Lab and for the U.S. Air Force for numerous years. And this library and API exists for various government off-the-shelf tools, including NRL Builder and Air Force IMOM. As mentioned earlier, our relationship with NASA is growing, where we are working to develop LunaNet, and further use cases are being determined, including Earth to Moon communications. With our partners, being a small business, this is extremely difficult. So we have deep relationships with our friends at Keysight, Ansys, now Synopsys, MVG, ETS, Viavi, and Enritsu, with our partner in Japan, Kozo Keikaku Engineering. And we have API integrators, namely Ansys SDK. And we are deeply collaborating with academics and with the US research groups, including NIST, for measurements and publications, and developing machine learning models and training data sets for various use cases, including MIMO and multimodal sensing. NASA has been driving a lot of the next generation innovations in communications with the development of next generation ray tracing, where we have the ability to model communications in complex terrain, including craters, and the ability to model complex physics, namely surface waves over terrain, and providing these services to NASA under the Small Business Innovative Research Grants and the awards that Remcom has been given over the past few years to be able to model, simulate, and develop communications for very difficult conditions that are presented on the lunar terrain. Furthermore, we are looking at correlation and validation of the JET 7 measurements that NASA and NASA's teams have performed on various craters in the Nevada and Arizona deserts, and providing those grounded correlations between the predictions that are made inside Wireless InSite, inside Remcom software, to measurements that NASA has performed. Moving into orbital communications into the lunar surface, this is a growing area that we're continuing to partner with NASA. In CAD and manufacturing, primarily with the use of full-wave simulation, the device design contains very complex mechanical structures supporting PTC Creo, supporting the use of Siemens NX and SolidWorks, allowing the user to import very complex geometries, including CATIA for automotive, and the ability to import Allegro PCBs in the BRD format with partnership with Cadence. And these are examples of how we do this in the ECAD space, where we have the mechanical plus the PCB being able to be simulated in full wave. Moving this into the MCAD world, where the PCB does not play a major role. In fact, this is primarily for antenna mounting and coupling on very complex structures, including vehicles used by the US military. Then looking at granular impacts of RF and EM energy on the human tissue, and looking at this at the granular level of 1 millimeter, including sub 1 millimeter resolution models of the human body. Supporting virtual population and NICT with our friends in Japan, using XFdtd to be able to look at exposure of the human tissue. With the past few years, where digital twins have become the norm in terms of representation of the real world environment, including outdoor, indoor, we have developed several workflows to be able to digitize large areas of urban, suburban, rural areas with the use of free maps like OpenStreetMap, working with vendors to be able to provide high quality grounded satellite imagery, including the effects of foliage, the presence of foliage, material properties on individual buildings, potentially down to several material properties representing one building, and the effect of localized communications within or surrounding private 5G and local campuses. The use of USD format is becoming a norm, with support from NVIDIA Omniverse, supporting USD import and export with Blender, and the utilization of such tools for moving into high-resolution CAD modeling. Digitization of indoor floor spaces is another area of growth, where we have over-the-air wireless testing performed in very complex indoor environments representing customer use cases, namely apartments, houses, offices, factories, etc., where physical testing becomes extremely challenging. And we have digitized real spaces using LiDAR, using scans, and using the ability to import and create floor plans by hand. Moving into localized effects of RF on the human body, we are looking at scans that are performed with ECG sensors on the body, looking at the effects of breathing, the effects of the heart rate on the breathing, as specified in this waveform, which is a superposition of two waveforms, including the heart rate and the chest. Localized motion of the human body, including devices on the body, namely a smartwatch, and the effect of the antenna pattern as it's at the body, the near field effects of the body on the antenna. So utilizing tools like Blender, OpenBIM, and NVIDIA Omniverse has become a norm. Capture methods are also very important, and this is typically done by our partners, but we have a pretty deep understanding of this topic, as we require certain types of behavior from CAD surfaces, namely the creation of triangulated surfaces, vertices, edges, to be appropriate for ray tracing and for full wave modeling. And this is a ever-growing area of knowledge, which requires careful experience and applying those to utilization of simulation. So the creation of the mesh is essential, and how the solver interacts with the mesh is important for digital twins and often overlooked because textures take over. So pretty pictures over accuracy. And we make sure that we are focused on the right aspect of digital twins, which is the representation of the triangles as appropriately as possible. So utilizing the United States Geological Survey for terrain, and then putting high-resolution buildings on top of that, and making sure that the mapping of the buildings to the terrain is accurate. For indoor maps, we have furniture placement and accurate representation of the indoor floor plan, the ceiling, the walls, the columns, and then the possibility of humans present in the environment while measurements are taking place or not. The use of novice equipment with our friends in Japan, with KKE, and the utilization of the digitization and conversion of those LiDAR maps to indoor floor plans is another growing and challenging area. Our friends at NIST and our partnerships with the US government has led to the measurements and publication of several efforts in the comparison of RF channel sounding and radar measurements from human gestures and utilization of physical optics, which we will briefly cover. So without validation, all of these claims are mute. So we need to move into the utilization of simulation with measurements and correlating those. And that really starts at the near field level with circuits, with components and manufacturable devices. And we would like to present this data from Motorola, as they were kind enough to let this be presented to the public, with the utilization of XFdtd for the design of antennas, the presence of the flex, and the antennas that the engineers have created with the matching, including meshing, very finely meshing these matching networks and the clips that connect and disconnect the antennas and ground the antennas. So you're looking at specific band behavior with devices in various conditions of, namely in free space versus hand left, hand right, phone call mode with the hand and the head. We have correlation within 1 dB RMSE in often cases. Presently, this is dated correlation data overlooking almost 1 decade. Presently, we have correlation even below 0.5 dB, in some cases 0.1 dB. Moving this into large-scale metamaterials, looking at surfaces produced by the Communications Research Center, the Government of Canada, the ability to 3D print and manufacture diffusers, grading surfaces, and using those in indoor environments where we have placed metamaterial, shining illuminating it with a transmitter, and then looking at the behavior of received power along this route. Because of multipath effects behind the wall, including internal reflections and potentially the presence of metallic columns, these internal reflections can cause discrepancies. As we move into multipath in the line of sight region, we see excellent correlation from this scattering surface. So this mathematical representation of the scattering from the surface was done in partnership with the CRC and put into Wireless InSite for large-scale studies, including outdoor and use of metamaterials outdoors. Human shadowing in correlation with the utilization of knife edge models, UTD, uniform theory of diffraction, for a use case where a user is walking between a transmitter and a receiver, is done at a fundamental level to prove out the validation of both the uniform theory of diffraction and physical optics, where the representation of UTD really happens in a simplified representation of the human body, potentially without legs, since in this case, most of the energy is passing through the head or around the chest. Simplified modeling of the body, and the use of UTD gives you fast but fairly accurate answers within 2 to 3 dB RMSE. And then we have the utilization of physical optics, where the full human body and extra multipath around the face, around the head, plays a critical role, and we get a better correlation within the 2 dB range of path loss. Looking at this for automotive, again, the same story, where we have 2 to 3 dB correlation for illumination of this vehicle from the rear end, where the radar line of sight is illuminating the back part of this vehicle, and the multipath is progressing through the undercarriage of the car, and potentially even illuminated by some blockers, rebars, and so on, and looking at overlap between, say, reflections from the front of the car, down to 1 dB, a couple of dB in the middle of the car, and so on. So again, this proves the utilization at 94 gigahertz across 8 gigahertz bandwidth of the physical optics solver. So now comparing all these methods together against each other, where full wave, going back to the initial chart where we saw the utilization of XFdtd against consumer electronics and near field design, and then asymptotic models for long-range communications. In some cases, any of these methods, if not all the methods, could be appropriately used, especially at 2.4 gigahertz, where you have the presence of a human body in a simplified room, and really validating all of these methods against each other. As the frequency grows, the asymptotics take over, the physical optics potentially for radar, and UTD potentially for large-scale communications, and some overlap between those methods for each other's use cases. So good correlation again, grounded in fundamental Maxwell's equations in full wave, and then applying most of the physics effects with ray tracing. So without machine learning and the generation of data, I think much of where we're headed the past 5 years and into the future is with development of novel methods for antenna design, genetic algorithm coming up with methods for 3D antenna design, using fitness functions for generation of arbitrary antennas for various use cases, including astrophysics, this study led by JPL and Ohio State, and continuing work on the optimization and reduction of the number of generations required to come up to an idealized genetic algorithm design, GA-enabled design. Looking at the latest research in this space is surrogate modeling with fast global search optimizations, married with the particle swarm optimization, and developing trust region techniques. So this is the next generation trust region, physical optics, apologies, not physical optics, particle swarm techniques, looking at the creation and the optimization of a 3D antenna. This is a earbud present with the human body, which is not being displayed here, a feed, and looking at the cost that it takes to do this with surrogate modeling, machine learning, 160 simulations to come to an optimized antenna, dual band antenna, versus traditional particle swarm requiring about 400 simulations. So significant savings of runtime and computer resources. This work is being led by our friends at Vanderbilt. This study highlights Technical University of Munich, where they are using an LLM in German to control and bring to live a stream and a radar inside their lab. And this robot inside this RF lab is brought to a specific test requirement to follow a specific path, and the creation of that digital twin is loaded based on the position of the sensors of the robot, and then multi-sensor fusion, including camera, lidar, integrated sensing, and comms, is being shown in this demo. So this is an ongoing area of research. As we mentioned earlier, the promotion of machine learning datasets, including the support for academia to develop models, namely DeepMinder, which has become the standard for ray tracing datasets for wireless communications, led by Arizona State and Dr. Ahmed Al-Khatib, utilization of wireless InSight for the past many years, and now the support for NVIDIA ray tracers, feeding those into post-processors, including DeepMinder post-processing, NeoRadium, and the 5G toolbox from MathWorks. So all of this really needs to come together as a cohesive workflow, and we're helping engineers build this out, not just at granular levels, which is required, but also for finer automation. So we're introducing the Fusion Studio software, which was announced at IMS in Boston a few days ago. And the utilization of these workflows really can be automated in terms of not just analysis of the soft analysis of the electronics device, whether that's in free space or on body, and then applying those into specific environments. That can be a radar in cabin, it can be a person walking inside the room, or vice versa, a combination of the two, or feeding those directly into a data set to generate receive power, impulse responses, and the output IQ. Further post-processing those into mass generation of appropriate information that can be fed directly from this Claude-driven, AI-driven workflow into channel emulation from Inritsu, from Viavi, from Keysight, or developing machine learning algorithms, namely breathing models, or developing range Doppler synthetic data for environmental testing of devices inside user cases. Beyond this, we are introducing the use of the chatbot with Claude to be able to generate outputs from full wave and injecting those into environments with the use of agentic orchestration, where users can bring in antennas from any source, measurements, full wave simulation tools, or create their own antennas and superimpose those into the environment and use advanced algorithms, namely reuse of those propagation paths and superimposing new antennas on top of that, including the ability to add motion, presence of humans, multiple humans, etc., into that scene, and automating through that and visualization of antennas within that workflow. So this is a simplified orchestration approach where users can either build out the environment where the scenes are developed, multiple projects, multiple antenna sources, multiple walking motions, and deploy those onto the cluster locally or on the cloud. And moving that into a chatbot as well, where we have a cloud mode where the user can chat instead of using the interface. So as these are growing, we are working very closely with RF engineers to make sure their needs are being met as they continue to take on further burdens without the resources that they should be allocated. Thank you for listening. You're welcome to reach out to us. We enjoy solving the hardest problems in RF and microwave, and we look forward to speaking to you further. Thank you.